Hey everyone, it's that math magician, and on this video we're going to take a look at Pythagorean triples. I'll introduce to you what they are, how they relate to the Pythagorean theorem, and how we can use them as sort of a shortcut to solving the sides of a right triangle. So let's dive right into this video with an example of a right triangle with sides of A and B as the legs and C as the hypotenuse of that right triangle. Now remember, Pythagorean's theorem is a squared plus b squared equals c squared. And that's a formula that we can use to help us solve for an unknown side of a right triangle when we know two sides already. So what I want to do is I want to give you a quick example of how we can use Pythagorean's theorem to solve for an unknown side on this right triangle. What I'm going to do is I'm going to go ahead and let a equal 3 and I'm going to let b equal 4, and I want to use Pythagorean's theorem to help us solve for this unknown side, our hypotenuse, c. So to use Pythagorean's theorem, I plug in 3 in for a, 4 in for b, so I end up with 3 squared plus 4 squared equals c squared, and now I can solve for c by just doing some arithmetic. So 3 squared is 3 times 3, which is 9, plus 4 squared, which is 16, and that all equals c squared. Well, 9 plus 16 adds together to make 25, which still equals c squared. I want c by itself, so I will need to take the square root of both sides. So c equals the square root of 25, and the square root of 25 is just 5. That right there is our final answer for C. We've now used Pythagorean's theorem to solve for the hypotenuse, and that hypotenuse is 4. Now what might stand out to you is that normally when we do Pythagorean's theorem, most of the time we don't end up with a whole number here. Usually it's a decimal number with lots of numbers after it because the number we're taking the square root of is usually not a square number. 25 is a square number. When I take the square root, I get a whole number as my answer, or an integer. What Pythagorean triples are, and what the point of this video is that there are combinations of sides for right triangles, where every side is a whole number. And we call those Pythagorean triples. And the reason why we call them that is because they often come up a lot when we're doing example problems, and they satisfy Pythagorean's theorem. So, one Pythagorean triple that we have, and that we've just shown, is the Pythagorean triple of 3, 4, and 5. That right there shows you that these are the three sides of the right triangle. They are all whole numbers, and they satisfy Pythagorean's theorem. That's what Pythagorean triples are. They're just three sides of a right triangle where every side is a whole number. And so you might be thinking, are there any more Pythagorean triples? Because what's really nice about these three is that if you see those two sides, for example, the 3 and the 4, we automatically know that that other side is 5. And there actually are an infinite amount of Pythagorean triples. And one way to think about this is, what if I were to take that triangle there and to dilate it to double its size? If I were to take this triangle and dilate it by a factor of 2, so that not both sides, but all sides are multiplied by 2, I would then create this new triangle where A is 6, B is 8, and C is 10. And that is another Pythagorean triple where, which I'm not going to do right now, but if I were to put it into this Pythagorean's theorem, it would still end up working. And this again is an example of three sides of a right triangle where all the sides are a whole number. So we can add that to our list here, 6, 8, and 10. And as I mentioned, there are an infinite amount of Pythagorean triples. There's actually an infinite amount off of this 3, 4, 5 triangle. A 3, 4, 5 right triangle, I can keep dilating these sides to create new sets just by multiplying those numbers by a different factor, right? I could multiply all of these sides by 3. A new Pythagorean triple would be 9, 12, and 15. So the 3, 4, 5 right triangle shows up a lot. And yes, you could always just use Pythagorean's theorem to solve. But if you can remember that 3, 4, 5 is a Pythagorean triple, it might just save you some time when you're working on some problems. Now there are, like I said, an infinite amount of Pythagorean triples. And I can't, on this video, show you all of those. But there is another one that does show up that is also quite common, almost as common as the 3, 4, 5 triangle. And that is when you have A is 5 and B equals 12. And if we want to find out what C is. So what I'll do for this is I'll actually show you one more time how Pythagorean's theorem works. We can solve for that side of C and figure out another Pythagorean triple. So I'm going to let A equal 5. So I'll have 5 squared plus B squared, which is 12. So I have 12 squared equaling C squared, right? We're trying to figure out what is that last number for this Pythagorean triple. So 5 squared is 25. 12 squared is 144. That all equals C squared. Now 25 plus 144, that adds to 169, which equals C squared. Remember, we're interested in C, so I will take the square root of 169, and the square root of 169, if you don't know that off the top of your head, you can always use a calculator. I'm using the free Desmos calculator that you can use online. I'm going to go ahead and hit the square root button, and I'm going to type in 169, and I see that the square root of 169 is 13. So I find out that that remaining side of that right triangle is 13, and that is another set of Pythagorean triples. Another set which is 5, 12, and 13. You'll notice that this is not the same Pythagorean triple as 3, 4, 5. It is not a multiple. It is a brand new set, and again, we can derive a lot of other sets from that Pythagorean triple. Again, Pythagorean triples are just a set of numbers or a set of sides where every side is a whole number or an integer. Again, if I wanted to create some more Pythagorean triples off this guy, I could just multiply all of these by 2. And so I would end up with another Pythagorean triple, which would be 10, 24, and 26, right? Just a zoom factor off of the 5, 12, 13. And what I want to really drive home the point for Pythagorean triples is that it's just a nice way of remembering a shortcut for solving certain problems. I'm going to go ahead and erase this example problem one more time just to show you how you could use this to help you solve for a missing side of a right triangle. So let's say I have that right triangle there, and that I know that my hypotenuse is 15, and I know that my leg right here is 9. And I want to figure out what this missing side is over here, which is x. Now, I could just use Pythagorean's theorem if I wanted to. There's nothing stopping me from using that. But what I can also do is look at those two sides, and since they're whole numbers, they might be a Pythagorean triple. So I look over here at my list, and I remember that the 3, 4, 5 triangle, when I had multiplied it by a factor of 3, it has another Pythagorean triple that's 9, 12, and 15. Well, since the 15 matches up with the hypotenuse, and the 9 is matching up with this leg, instead of doing Pythagorean's theorem, I automatically know that x here equals 12. Because the 9, 12, 15 triangle will always be those same sides as long as you can show that those two sides that you have are filling in those spots there. That's what Pythagorean's triples are. They're just sides of a right triangle where all the sides are whole numbers. It's that math magician, and I'll see you on the next video.